Hello, ladies and gentlemen. My name is Jan-Iwo Jäkel from the Institute for Construction Management, Digital Engineering and Robotics and Construction. And today I want to present you our paper, A Concept of Automated Damage Management for the Maintenance of Bridge Structures as a Life Cycle-Oriented Approach. First, I want to show you our today's agenda. In the first chapter, I give you a short introduction and show you the research target. The second part is the presentation of the methodology of the paper. Then I'm going to show you the state of the art. After that, we are doing the development of the approach. And in the end, a short conclusion, research limitations, and our future research topics. Bridge structures have a special significance for the economy and society in Germany and Europe. The target is to provide a resilient infrastructure, but this is connected to challenging tasks with multidimensional complexity. Predominantly in the bridge maintenance management, we are executing manual inspection processes with a low degree of automation. This leads us to a reactive bridge maintenance management at the moment. So by linking digital methods and new advanced technologies in the area of inspection processes, especially in the damage management, we could increase the process efficiency and the process automation in this area. Additionally, by using open data formats, we could enhance the interoperability and collaboration along the whole value chain in the bridge maintenance. So our research target in the paper is to develop a concept of an automated damage management for the maintenance of bridge structures as a lifecycle-oriented approach. We are combining robot systems, digital methods, and AI to increase the automation in damage detection and damage management, focus of the entire life cycle. We are using a common data environment and open exchange formats to support and standardize the collaboration of all involved parties in the maintenance processes. Here our methodology, we start with the definition of the state of the art, connected to a literature review in the fields of mobile robots on construction sites, mobile robots on bridge inspections, and automated damage detection. Further on, in the second part, we are developing our concept by using mobile robots, digital bridge models, a common data environment, artificial intelligence, and open data formats. And in the end, we are implementing our concept in a first mock-up and demonstrate the basic feasibility. So in the first part, we executed a literature review in these three areas. The mobile robots on construction sites, mobile robots for bridge inspection, and automated damage detection. For mobile robots on the construction sites, we identified the different usage of wheeled, legged, and climbing robots on construction sites in the current state, and the robot systems are mainly used for data acquisition and process monitoring. These robot systems operate mostly as a mobile support system for laser scanners and cameras. In the next field, mobile robots for bridge inspections, we identified that mostly UAV systems, climbing robots, and special hybrid robots are used for the inspection processes and inspection of damages on complex bridge structures. Mostly these systems are carrying camera systems to acquire the images. And as a total and all conclusion, the robot systems can significantly increase inspection process of bridges. In the automated damage detection, the other researchers mostly use artificial intelligence for the further processing of the recorded inspection data, the main use of artificial neural networks for the image interpretation could be identified, and that the use of AI for identifying damages in pictures has a huge automation potential for the whole process chain. In the end, we identified a lot of individual systems which have already a high degree of automation, but till now there's no consideration of the whole process chain in the damage management life cycle. So our approach is to connect these systems in an interoperable way by using open standards and a CDE as the central part of the whole concept. In the next step, we developed our concept. We linked the further development in this area. We used digital technologies with a high degree of automation. We used open exchange format to achieve interoperability along the complete process chains. We used a common data environment as a central element in the single source of truth approach. And in the end, here's our process model, which we developed. Our concept is mainly divided into 5 subparts: the provision of the digital model, the preparation of the inspection tour, the image acquisition, the image processing, and the damage detection. And in the next picture, on the next slide, I'm going to give you an easier introduction into our concept. As the main part of our concept for automated damage management in a lifecycle-oriented approach, we have our cloud computing system. In this cloud computing system, we have implemented the common data environment. So the common data environment is our central data hub, our single source of truth in the whole process chain. This common data environment stores all relevant data in an IFC format as a digital model. And the common data environment is also linked to a damage library. These damage libraries has acquired information and for standardized damages like cracks, holes, or gravel pockets, which we later use for the classification and semantization of the AI. In the first step, we provide the digital model and transfer the digital model from the common data environment in IFC format into a Unity environment. In this Unity environment, we planning our inspection tour in a virtual simulation environment. We are defining the route and then simulate it and test it. After a complete test, we transferring the inspection tour data via a ROS interface as a JSON data file into the real robot. Then we are starting our next step, the image acquisition. So the robot is running around the tour and is taking pictures in predefined waypoints. These pictures are, after the finishing of the tour, are stored in a raw data storage, and after that transferred back to the cloud system, where an AI system is going to classify, interpret it, and semantize these pictures with further damage information. And these damage informations are going to be transferred in a BCF format back into the common data environment. After I showed you our concept in 2 different models, I'm going to present the mockup implementation. Here, the 2 parts, provision of the model and preparation of the inspection tour, where we use the Unity environment as a within ROS interface. For the tour planning, the tour was planned by defining waypoints and using the nav mesh function for the tour planning. After that, we transferred the whole tour into a JSON file format and transferred it into the robotic system. After the robotic system executed the pre-planned tour and shot the photos on the predefined waypoints, we tested, or we developed an AI system as a convolution neural network to identify damage patterns. In this case, we trained our AI algorithm to identify holes. Here in this case, we did a small mock-up, a small prototype, where we identified and recognized damage holes in the wall of the bridge. And after the identification of the holes, we also can make the semantic interpretation of the damage, that we can implement further damage information into the damage file. These damage files, after the semantic interpretation, are going to be transformed into a BCF format, and with the BCF format, we transfer the whole damage information package back into the common data environment, where the system can directly implement the BCF format and with a viewpoint on the right location, transmitted out of geographical coordinates of the image acquisition. And with the identified damage, we can transparently forward the tracked BCF issue to the responsible project participants. Here's a small outtake of the extension of the BCF format with damage data, with our damage information. So in the end, the paper presents a holistic approach out of an automated damage management focused in the entire life cycle. The concept illustrated the basic feasibility of the process chain by its implementation in a mockup. By linking digital methods and technologies, we can increase the degree of automation in damage management, and the concept increases the interoperability and collaboration in damage management through the use of open data formats and the integration of a common data environment as a single source of truth. Till now, we just implemented the individual process paths into a mockup and tested them, but as a limitation of the concept, we need to mention that till now there's no validation of the whole system. It's just a concept with a small mockup, so we need to validate this whole concept by prototyping it under the consideration of all interfaces and the whole process chain. And until now, the convolutional neural network has so far only been trained to recognize and semanticize one type of damages, in this case the hole. We need to develop it to recognize more different damages like cracks, etc. And for the true planning approach, it only has been tested in a virtual simulation environment. We also need to validate our ideas of the tour planning approach. So for the further research, we're going to prototype it and going to execute the whole validation of the individual technical components in all phases. We will validate also the interfaces to verify the interoperability between the different systems. We need further development of AI system, and after the whole validation of the approach for the bridge structures, we could also transfer it to different infrastructure systems like tunnels and dams. Thank you very much for your attention, and if you have further questions to the research topic or our research in our institute, please contact me via the shown email. Thank you very much.